You are welcome, students and viewers. In this video, we are going to look at this topic, equivalence relation. Relation and partitions. Well, recall that a relation R from a non-empty set, say X, to another non-empty set, say Y, is called an equivalence relation if one, we have R inverse is contained in R. Okay, first, the identity relation is contained in R. 2, the inverse of the relation is a subset of the relation. 3, if you have for all AB in X, because a relation now is from X to Y, for all AB in X, you have for all ABC in X, if A is related to B and B is related to C, okay, B is related to C, this implies A is related to C. That is transitivity property. And this is the reflexive property, reflexivity. And this is what? Symmetric property. Symmetric property. So if the relation is symmetric, reflexive, and transitive, we call the relation what? An equivalence relation. And what does an equivalence relation do? An equivalence relation induces a partition on a set. So what this relation does is it partitions a set into equivalence classes. This is a set, it partitions the set into equivalence classes. So every relation, every equivalence relation, so partitions a set on which it is defined, or every equivalence relation on a set A, so partitions A into equivalence classes. Equivalence classes. Where if you have A in A, the equivalence class of A is denoted, okay, is denoted by So this is the equivalence class of A. That means the equivalence class of A, and it is defined by X in where? X in A, such that what? X is related to A. So meaning the equivalence class of A contains all the elements of A that are related to the element A. So, uh, so you see, the equivalence class, the equivalence relation now will partition this set A into equivalence classes. These are the equivalence classes. So, so elements will be here in the equivalence class of A if and only if it is related to E. If an element B is not related, is not in the equivalence class of A, it means it is not related to A, and we write something like this. A intersection the equivalence class of B is what? Is empty. Once A and B are not in the same class, is not in the same, they are not in the same equivalence class, so we write A intersection B, the equivalence class of A intersection the equivalence class of B is equals to empty. And you see, this equivalence relation induces a partition on a set. So given any equivalence relation, you can always find a partition that partition the set into equivalence classes. Now give me a partition, I can always find an equivalence relation that defines such partition. Let's take example. Example 1. Okay, let R be a relation, on the set Z of all integers defined by, so we define this by A is related to B if what? A minus B, if A is congruent to B modulo N. That is, N divides A minus B. So A is related to B if N divides A minus B for a fixed integer N coming from the set Z. No? For any fixed integer. So prove that this relation, prove that R is an equivalence relation. Equivalence relation on the set of integers. Now the proof. To prove that, we just make sure that we see that R is reflexive, symmetric, and transitive on the set Z of all integers. So now, for reflexivity, prove it step by step. To prove reflexivity, we see that A for all A in Z, that is for all integer A, we see that A minus A is equal to 0. This is an integer. But N divides 0. Pick any fixed integer. That fixed integer actually 0 divides such an integer. Sorry, what I mean, fix any integer, then that integer 0 is divisible by that integer n. So that what? A is, so we write this as A is congruent to B modulo n. So that is A is congruent to B modulo what? N. A is congruent to A. Every element is related to itself. And therefore you see that R, A is related to A. And that we have proof reflexivity. Now for second item, the symmetric property. Symmetric property. We have to check that too, even though we mustn't write, but for guidance, let's write. So, so suppose A is congruent to B modulo n. And what does that mean? This implies A minus B is divisible by n. That is the meaning. And what we are saying is n divides A minus B. A minus B is also an integer, since A and B are integers. So we see that n also divides B minus A. So it divides the negative of what? A minus B. So if you have n divides A minus B, n would also divide minus the negative of A minus B. And that means n divides B minus A. And what does that mean? That means A, so that means B is congruent to A modulo n. Which means what? B is related to A. And here we have A is related to B. So A is related to B implies B is related to A. We have proved the symmetric property. Now the transitive property. The transitivity now. So suppose what? A is congruent to B. So suppose A is related to B and B is related to C. Implies what? That means A is congruent to B modulo n. And B is congruent to C modulo n. And that implies what? That implies A minus B is divisible by n, and B minus C is also divisible by n, meaning n divides A minus B and n divides B minus C. So now, a number n divides two integers. Definitely, this number must divide the sum of these two integers. So what we are having, we say this implies that n divides the sum A minus B plus what? B minus C, because n divides each integer, A minus B and B minus C. And so n divides, so if you add, you have what? Here you have A minus B plus what? B minus C. And that implies what? So that implies n divides what? A minus C. And which means A is congruent to C modulo n. And that means what? That implies A is related to C. So we have transitive property here. A is related to B and B is related to C, implies at the end A is related to C. Transitivity happens. And so the relation and so the relation of being congruent modulo is an equivalence relation. So the congruence modulo relation is an equivalence relation. And what does it do? This equivalence relation partitions the set of integer into equivalence classes. Let's be more specific and take some example. More specifically, you have example 2. Let R be a relation on Z, meaning from Z to Z, defined by A is congruent to B modulo 3. If what? If 3 divides A minus B. So it is clear from the previous example that this is an equivalence relation. This is an equivalence relation on the set of integers. And what does it do? So it partitions the set of integers. It partitions Z into equivalence classes. Equivalence classes. How many equivalence classes? 3 equivalence classes. So it partitions the set of integers into 3 equivalence classes. First of all, you will consider that in our proof, the first item is reflexive, and the reflexivity says what? A minus A is equal to 0. So, since it is equal to 0, it means we are going to be looking at the equivalence classes left. When we are going to be looking at the equivalence class of 0, that is the remainder when A minus B is divided by 3. So into equivalence classes. So now, because we know what the equivalence class means, so the equivalence class of 0 is going to be when will a remainder 0 be seen when a minus b is divided by 3. So we start the equivalence class of 0 will contain 0 and all other multiples of 3. So if you add 3, you get 3. You add 3, you have 6. You have 9. You have 12, and so on. Here, when you add 3, you subtract 3, you have minus 3, minus 6, you have minus 9, and so on. So this is the equivalence class of 0. So if I like, or if we like, we can write it as the equivalence class of 3. It is the same as the equivalence class of 6. Any number you pick from here will serve as the representative for this class. So the equivalence class of 1, this is equal to, so 1 is inside, it is in its own equivalence class, and subsequently if you add 3, so if you add 3, you have 4, add 3, you have 7, add 3, you have 10, add 3, you have 13, and so on. So subtract 3, you have minus 2, subtract 3, you have minus 5, subtract 3, you have minus 8, and so on. The equivalence class of 3, meaning the remainder 3, when a minus b is being divided by 3. So 3 is in its own equivalence class, and is it 3? So not 3. So the equivalence class of 2, because we have talked about the equivalence class of 3. Sorry about that, mix up. So 2 is in its own equivalence class, and subsequently if you keep on adding 3, so you have 5, add 3, you have 8, add 3, you have, if you add 3 to 8, you have 11, you have 14, add 3, you have 17, and so on. So here, subtract 3, you have minus 1, subtract 3, you have minus 4, subtract 3, you have minus 7, and so on. So you see that this equivalence relation actually partition the set of integers into equivalence classes. These equivalence classes are the equivalence class of 0, equivalence class of 1, equivalence of class of 2. So if you want to understand that this is actually a partition of the set of integers, you see that these classes are non-intersecting. Here is 0, here is 1, here is 2. So you see, if you are counting the integers, you have minus 9, minus 8, minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Likewise, 15, 16, 17. That's how it continues. And if you check the union of all these classes, it gives you the set of integer. So definitely, you see that the set of integer is the union of all these classes, equivalence classes, the equivalence class of 0, union the equivalence class of 1, union the equivalence class of 2. And so, this equivalence relation actually this equivalence relation actually defines a partition on the set of integers as we have seen. Okay, so what relation or what partition will imply equivalence relation. Let's give example. Example now. Example 3. You see the relation in a university, as in a university setting. In a university setting, see the university at large is the biggest collection we can have in that collection. So there are faculties, and these faculties are subdivided into departments. And some departments are even subdivided into programs. So you see that two students will be related if and only if they belong to the same department. So in a university settings, students of a faculty, let's say faculty, are related if and only if they belong to the same department. The same department. So now, the relation of being in the same department is an equivalence relation. So the relation of being in the same department is an equivalence relation. So where students will be related if and only if they belong to the same department. And this relation will partition the faculty into equivalence classes. For example, let's take the Faculty of Science. For example, we have Faculty of Physical Sciences, So this as a whole, the Faculty of Physical Sciences, to denote by this is a faculty. So this faculty will be divided into, you see, you can have mathematics department, you can have the chemistry department, you can have geography department, you can have geography, so you have the geology department, so you have physics department, and so we have talked about chemistry here, so physics department, and so on. So the relation of being in a department will partition the faculty into equivalence classes, whereby two students belong to the same equivalence class if they belong to the same department. Two students are related if and only if they belong to the same department. And this induces, this relation of being in the same department induces a partition on the set, namely the non-physical science faculty, to partition it into equivalence classes. And these equivalence classes are known as the department in the faculty. We can also give a real life example whereby two people are related, for just find two persons, they are related if they belong to the same family. So, and this relation of being in the same family is an equivalence relation. We can also give another example that where you find any two people will be related if and only if they have the same blood group. So this will partition the whole people in the world into equivalence classes, This is the whole world. It will be partitioned into equivalence classes. And these equivalence classes will be the class containing the O positive, O negative. And this, another partition will be A, another partition will be AB, and another partition will be B. So now this relation of being in the same blood group has partitioned the whole world into equivalence class, where every individual belongs to one class, no two. So you see that there is no intersection between, there is no any individual with blood group O and at the same time with blood group A. No, you have either O, A, AB, or B. It doesn't matter whether we have O positive, O negative, B positive, B negative, A negative, and so AB positive, AB negative. But this has partitioned the whole world into equivalence classes, where